DNS, the domain name system, is like IP and TCP, one of the most important protocols in the TCP/IP protocol suite. Then this, in fact, is not only a protocol; it's in fact distributed application, a distributed service with some kind of architecture, and within that application architecture, we have a particular protocol called DNS. There are several RFCs that are that specify different aspects of DNS. For instance, the RFC 1034 specify the protocol, the DNS protocol. In fact, DNS is very useful because we don't remember easily numbers. For instance, if I ask you which is the IP address of the web host of the Fachhochschule Dortmund, I'm sure that you don't know, or you couldn't remember easily that number. For instance, this IP version 4 address of the website of the Fachhochschule Dortmund. But I'm sure that you remember easily the name. That is, for instance, this one, www.fachhochschuledortmund.de. Then, in fact, DNS was introduced to assign names to IP addresses. In order to manage this association between addresses and names, because we need to manage a large number of names, and at the same time allow the organizers, that is the different authorities that need to establish that assignment. In for instance, the Fachhochschule Dortmund is an authority, but there are several different organizations, that is, for instance, companies, universities, government, and different domains of authority that need to establish that relationship between IP addresses and names. Then that's why we use in DNS a hierarchical structure in order to permit to manage that large number of names and that large number of different communities of name authority. The domain name then consists of individual name labels, which are separated by dots, one name from the other. For instance, www.fachhochschuledortmund.de or those other names. I'm sure that you are very familiar with that kind of names. Then, in fact, the most important function of DNS is to resolve the name. For instance, when we type some name as one of those, we need to get the IP address associated with that name. Sometimes one name, one DNS name would be related with one or more than one IP address. For instance, if in the case of Technische Universität Dortmund, we receive, for instance, two addresses. Then, for instance, in that case, the web browser could choose one of those addresses and try to access to the website of TU Dortmund. In other cases, the DNS system could respond with different IP addresses depending on the context, on the scenario, on the day and time. And in that case, we could perform some kind of dynamic DNS resolution in order, for instance, to balance load between different web servers. This is simply to mention that in different systems there are always one function, one system call, for instance, like this one, get host by name, that when we use this function and we pass as an argument the name, this name, we could get the IP address associated with that name, and in that case, the resolution of this association is performed using the domain name system. Then, in fact, the DNS is, in fact, more than a protocol, it is an architecture. It is a single distributed database. It is queried in client-server mode. The client is called resolver. The server is is distributed, and we will see that there are different roles of or different types of servers. The database is distributed among many individual servers, which form a federation of nodes that collectively provide the DNS service. It's important the DNS service is implemented in a distributed, not centralized way or manner. Registrations, cancellations, and modifications to the data, when we call about the data, in fact, is for instance, the data, the registers of information that relate, for instance, a name with an IP address. But there are more other pieces of data that are stored in that single distributed database. We will talk about that when we mention the resource records. Then the data is divided into parts called zones. The data stored in that single distributed database is called zones. For each zone, an administrative entity, that is an authority, is designated that has permission, that is authority, to modify data contained in the zone. The DNS data is structured according to a hierarchical model, a tree, to organize the data. For communication between client and server, between resolvers and servers, in fact, a specific protocol is used called DNS protocol, whose messages are transported typically via UDP, but TCP is used, and TCP is used particularly to update the data information stored in the secondary servers, named servers. But we will see that in some minutes. Then remember the DNS protocol, the domain name system protocol, is used for communication between client and server, that is between resolver and name servers. A specific protocol then that is transported over UDP and TCP. In order to perform the DNS lookups, that is the resolutions, the name resolutions, the resolver query information. Typically, for instance, query the IP address associated with the name, with some particular name. And in that case, typically we use, we encapsulate the DNS messages into the UDP datagrams. But we could transport the DNS lookup over TCP/IP. Is less frequent. Is less frequently used the TCP. Typically, we typically use UDP to transport DNS lookups. DNS zone transfer, in fact, is used when the secondary server updates the resource records from the primary server, and in that case, the DNS messages are encapsulated within TCP, and the reserved port in both cases, in the cases of DNS lookups and in the cases of DNS zone transfers, the reserved port in UDP and in TCP are 53, the port number. Well, in this illustration, we could see in fact, the DNS service that could be a query, but we could query some IP address associated, for instance, with the name from the client, that is the resolver. For instance, when any user of the internet is using this computer and type name, typically full qualified domain name, that is a name, a DNS name, the resolver ask or query the IP address associated with that name to the DNS service. The DNS service then take this query and answer with the DNS response indicating which is the IP address associated with the FQDN that is specified in the query. In this cloud of the DNS service, there are multiple servers, not only one server. Well, then, in order because this subject is very complex, it's important that we need to explain, and you need to learn different aspects of the DNS architecture. We need to talk about the namespace, that is the concept of the full qualified domain name, an FQDN, full qualified domain name, that is in fact the DNS name, commonly the DNS name, the difference between domains and zones, to clearly understand the concept of zone that is slightly different from the concept of domain, to learn to understand what RR, that is resource record, mean, and which are the different types of RRs or resource records that the domain name system could handle. We need to talk about the name servers and the resolvers, the different types of name servers. We need to talk about the queries, the resolution queries that could be recursive or iterative queries. And finally, for instance, in order to synchronize the primary the secondaries with the primary servers of a typical zone, we need to perform a zone transfer. Then those are all the topics, all the subjects that we need to learn in order to understand what DNS is. Then the first important concept and terminology that we need to talk about is the namespace. The namespace, in fact, is that is all the data stored in that single distributed database is structured according to an NRE, unbalanced lexicographic tree, or simply a tree, a namespace tree. The nodes of the tree have labels. There is a standardized way of naming each node of the tree. The sequence of labels obtained from traversing the tree, starting from the node towards the root node, is used. Typically, we start from the node to the root. That is, the root is in the right side of the name. The labels are concatenated by separating them with a dot, and the dot ending is included. In this case, there are typically some examples. I didn't write the last the ending dot, but in fact, in any DNS message protocol message, the ending dot is indicated. Then the FQDN, the full qualified domain name. In fact, for instance, this one is a FQDN. Remember, always the ending dot is specified, in fact, in the protocol message. It is a sequence of labels separated by dot in ending with a dot. Each label could be formed by different letters in capital or in upper or lower case. Is in fact insensitive. Any number and the dash character. Some other characters are permitted, but at the original, at the first specification, only those are the characters that could be used to write a label. The maximum label size is 63 characters. In fact, simply in order to understand this, the encoding of the label is performed with the packet string, and that is a string where the the size or length specification is encoded in the first character, and that's why in fact the label could have at the maximum 63 characters. Then this is the typical example, the name of the website of the Fachhochschule Dortmund. We don't confuse with this concept, the FQDN, with, for instance, an email address or a website address or a website URL. Although in both cases the element contains an FQDN. Typically, the mail address of Fachhochschule Dortmund or the website of Fachhochschule Dortmund both contain this FQDN, but this is not an FQDN, and this is not an FQDN. This is an email address, and this is a URL, a unique resource locator. The FQDN, the full qualified domain name, has a particular hierarchy. That hierarchy, the FQDN has different parts. Typically, the name, the host name, or the name, simply the node name, a subdomain name, a domain name, and a top level domain name. Each of one could be formed with one or more than one label. The case of subdomains or of domains or domains. Root domains, in fact, there are several root servers. For instance, a.rootservers.net until m.rootservers.net. Those are the main zones that administer what we call the top level, the root domain. And behind the root domain, we have the top level domains. That is, the top level domains are just before, just under the root domain, and typically we know those top level domains as com, edu, gov, net, and in that case is a division based on the type of organizations, or mill and others. But in the evolution of internet appear later, for instance, the top level domains that identify different countries. Then, for instance, for Deutschland, FR for France, ES for Spain, AR for Argentina, BR for Brazil, UY for Uruguay, CH for Switzerland, Conférence Helvétique, or for instance, CL for Chile. And there are several different top-level domains to identify the different countries. This is a typical illustration of this name tree. Then the root level, the top level domains, and the subdomains, and subdomains of subdomains. Typically, different layers of organization. Each label, in fact, we will see that each label is administered by a different entity or different authority, and that's why we we don't talk about domains, but about zones, administrative zones. In order to manage, that is to administer that space, that hierarchical namespace, the ICANN, the Internet Corporation for Assigned Names and Numbers, and the IANA manage these top-level domains and assign domains to organizations. For instance, Germany, the assignation of different names before under DE, under top level domain, the top level domain DE from Deutschland. You have in fact this organization called the DENIC, DENIC. NIC comes from Network Information Center, then Deutschland Network Information Center, and this is the URL, and in fact this is the FQDN associated with that organization, that website organization. The organization may then independently manage the labels below its subdomain. For instance, the NIC will manage subdomains under the top-level domain. For instance, one of the subdomains could be Fachhochschule Dortmund or TU Dortmund. Either the next label is a computer name or the organization divides its domain into further subdomains. The Fachhochschule Dortmund has the subdomain Fachhochschule Dortmund further subdivided into, for instance, those subdomains under Fachhochschule Dortmund. And these subdomains are then managed by the institutions mentioned in those labels. That is, that way, the DNS permit the distribution of authority in the assignation of names. The following table lists some of the top-level domains. Typically, 80 for Austria, CH for Conference Helvetique, that is Switzerland, B for Deutschland, Germany, ES for Spain, España, FR for France, and so on. And in 2000, it can introduce more top-level domains like .aero, .biz, .top, .info, and other top-level domains. Then the difference between the concept of the domain and the concept of zones. A domain, in fact, is the totality of descendant nodes of a certain node. That is a subtree. That is the concept of domain. But a zone is not a domain. A zone is a portion of a domain administered by an administrative entity. The boundaries of the zones are set by how authority is partitioned and distributed over the distributed database. For administration, the single DNS tree is divided into zones. The administrative entity that has authority over a portion, that is a zone of the namespace, can add, remove, or change labels within that zone. That is the concept behind that terminology. Zone, administrative zone. Each administrative zone has an authority, an administrative entity that is able to add, remove, or change labels within that zone. The zone begins at a certain node and includes all nodes descendant from it, except nodes belonging to subzones whose authority has previously been delegated to other entities. Then, in order to separate two different zones where one zone is under another zone, we need to perform a process called delegation. And the delegation process could relate could establish a relationship between two different administrative zones where one zone is a child of the other. But the child zone is not administered by the administrative entity of the parent zone. This is something that you need to understand clearly. In this illustration, we could see, for instance, this is typically the name, the full qualified domain name of the Faculty of Engineering, Facultad de Ingeniería of the University of Buenos Aires in Argentina. Then, in fact, there are four levels. The root level, the top level domain, and subdomain, and a subdomain under that subdomain. Then root, the Argentine zone administered by, for instance, in the case of Argentina, by the organization called NICR, Network Information Center Argentina, at the University of Buenos Aires, and finally the Faculty of Engineering of the University of Buenos Aires. The administrative entity that administer the names that finish with fe.uva.r, in fact, is an administrative entity different from the administrative entity that administer the names of uva.r and so on. And that is, in fact, the difference between the concept of domain, that is, a domain is a subtree. For instance, uva.r is a subtree, but the administrative entity that administer uva.r is not the administrative entity of the fi.uva.r. Then this is another way to illustrate the different concepts behind the terminology used of zone. Then the zone of for instance, the name of the top level domains are administered by the root zone. The names under the subdomain names under a particular top level name is administered by a top level domain, and so on. This is another example, another illustration that shows the division of the name tree in different administrative zones. Well, this is a different, another aspect that we need to understand related with domain name service. The concept of name servers and the concept of resolvers. Organizations with their own domain must maintain a DNS server that converts the domain names of that zone into, for instance, typically IP addresses. This is necessary so that all computers of the internet can convert the symbolic computer names of an organization into IP addresses without which communication is not possible. That's why I explained previously that DNS is as important as IP and TCP. Without DNS, the internet couldn't be function. Couldn't function. In order for a host to participate in the DNS, they must use a resolver. When a host need to query some information to DNS, in fact, it is a piece into the host that is called domain name resolver. This resolver software makes a request to the local domain name server to translate domain names into IP addresses, typically. Either the necessary information is available in the local name server, or it must consult other name servers in order to provide the desired implementation. This is a typical illustration where we see that in a host, this line separates the host from the network. Within the host, a user program asks the information, for instance, in order to associate an IP address to a name. And that's why the user program need to call the resolver. Typically, for instance, using a get host by name. The resolver then queries, perform a DNS query across the network to the DNS system. In fact, the DNS system, in fact, responds with DNS response, and this information is bring to the user program. For instance, a browser or a mail tool or other kind of user program in that host. In order to avoid too many queries, same queries across the network, the resolver could store this information in a memory cache, in a buffer, in a local buffer called DNS cache. And this is to avoid too many queries that in fact are exactly the same queries across the network, and avoid the overload of not only the network but the DNS system, that is the different name servers. Remember that in that case, this lookup is performed over typically UDP, and the port, the reserve port in the side of the name servers used is the 53 port number. Then the entity that has authority over a zone is responsible for maintaining the DNS servers corresponding to that zone. That is authoritative servers. Then there are two types of authoritative servers. The primary, only one server in each zone is the primary server, and typically one or more authoritative servers are secondaries. The secondaries update their information automatically, consulting the primary. So we will see that there is a resource record called SOA, Start of Authority, and based in the information in the SOA SOA register, will perform or not zone transfer in order to update the resource records contained in the secondary server from the primary server. Note, on the client side, the resolution is usually mediated by a special server called a recursive and caching only name server. But in fact, often this name server has no authority over the different zones in the DNS, in the internet, in which no information about any zones is configured. Caching, if it's caching only name server, that name server it has no authority over a zone. In these servers, only the IP addresses of the root name servers are configured. Remember that there are several root level name servers, and in fact we typically configure only those root name servers in caching only name server. Well, in this case, in this illustration, in this figure, we could see in fact the network, for instance the internet, and we could see that here we have a host, any host with the typical user. In that host there is a name resolver that need to know for instance, typically the IP address associated with the a name, a full qualified domain name, then the name resolver will query the information to a local name server. That local name server could be a recursive and caching only name server. And this name server will ask different authoritative name servers, starting typically with the root level, and after that the top level domain and subdomain level name servers. But in fact, there are typically in the internet a lot of different zones, and each zone has his his authoritative name server. Remember that authoritative name servers are the name servers that contain the resource records, that is the information, the DNS information of each zone, where that administrative entity has authority to add, modify, or delete information in that portion of this single distributed database. And in the side of the authoritative servers, we could see that there is each zone has at least has only one and only one primary server. Any zone, for instance, the root zone, the top any top level domain zone, or any domain or subdomain zone has one and only one primary server. But the primary server is not only the only authoritative server. There are other authoritative servers called the authoritative secondary servers. Any zone need to have at least one primary server and one secondary server. Typically, any zone has one primary server, but typically more than one secondary server, in order to offer high availability service to the internet. Then what is important to know is when the resolver asks the cache only name server here, and this name server asks something to one authoritative in zone, it's not important if this primary server is not available. What is important that at any time, any authoritative server of a zone could respond to any query from the internet. Now we need to talk about different types of queries. Then there are typically recursive queries and iterative queries. Remember, typically this is a host with a user using a program like, for instance, a web browser or a mail tool. This program needs to get some piece of information, like the IP address associated with the name, with the full qualified domain name. Then this program use the resolver. The resolver then perform a query, a recursive query, to the name server that is configured as the DNS server in this host. Then, in fact, what happens is that this name server will see if the information requested by the user is stored in his local cache, and if not, the name server, the local name server, will ask for that information to, for instance, a name server, for instance, typically the root name server. And if the root name server hasn't the information, the root name server, we will offer the information about the name server that could have authority over that name or over that full qualified domain name. And then the name server will perform another iterative query to the typically the child name server. For instance, this could be the root name server, this could be the top level domain server, or this could be a top level domain server, and this could be a domain server, and so on. And in that way, all the DNS architecture will exchange different types of queries. The recursive queries like this, and the iterative queries. In the iterative queries, we obtain the information that we need, or we obtain the information about the name server that we need to ask for the information required. Once this name server obtained the information required by the original query, will answer that query with that information. Then if you see there is a number that shows the sequentiality of those messages. This message is in fact the message when the program asks across, for instance, the system call get host by name, the IP address of a particular name. The resolver then asks that information to the local name server. The local name server asks this information for instance, the root server. The root server answer to the local name server with the information in order to retrieve or ask that FQDN to another name server, and then, for instance, this name server asks for that name to this name server. If this name server respond with the answer with the information required originally by the recursive query, then the configuration this name server will answer to this recursive query to the resolver, and finally the resolver bring this information to the user program. Remember that in the case of this local name server, this local name server will store in the cache the information obtained in each of the interactive questions or queries, and the resolver will store in a cache this information in order to avoid to ask for the same piece of information at least during a period of time. That is the period that the information could be stored in the cache. Here is another illustration where we could see the name resolver, the local name server, and the authoritative servers of different levels of root level, of top level domain, of domain and subdomain. Then We will see typically that between those, the queries are typically recursive, and between those, typically the queries are iterative. Typically, the root servers and top-level domain servers don't accept recursive queries, only accept iterative queries. That is because those zones are only zones that offer information about the zones under that branches of the DNS tree. This is another illustration that shows how recursive and iterative queries are used in order to obtain, for instance, the IP associated with this FQDN. Then the resolver asks to the local DNS server for the information associated with this FQDN. For instance, typically the address associated with this FQDN. We will see in some minutes that this information is stored in a resource record of type A, or of type 4As in the case of IP version 6 addresses. Then this resolver asks for the resource record A associated with this FQDN. Then the DNS server, the local DNS server, will ask for the root server for that information. The root server simply responds with the address, the name and the address of the server that administer, that has authority over the zone.com. Then this DNS server will perform another iterative query to the name server of the zone.com. This name server will answer with the name and IP address of an authoritative server in the example.com zone. Then this local DNS server will query for the resource record type A associated with this FQDN to this name server, and finally this name server that is the name server that has authoritative is authoritative over this zone, will answer with the resource record A associated with this FQDN. Then this DNS server will store that information, that is the RRA associated with this FQDN in his cache, and answer with that information to the original recursive request that this DNS client sent. Well, then now we need to talk about the resource records, that is the RRs. Then remember that the DNS, in fact, is a single distributed database. That database consists of several different resource records. Each resource record is stored in typically in a zone, an administrative zone, in an authoritative zone in the internet. Any resource record is member of a zone and couldn't be couldn't pertain to more than one zone. Then there is only one and only one of administrative entity that has authority over that RR. Any RR, any resource record, then has a name that is a fully qualified domain name. The length of this name is variable. There is another field associated with that record that is called type, and typically is coded with 2 octets. Then there are different types of RRs. Typically, for instance, A for the association between a fully qualified domain name and an IP address. There is a class that is coded with 2 octets, and typically in the case of internet, we always use the class IN from internet, IN. Any resource record has a time to live. The time to live is a 4-octet number, and specify the number of seconds that this resource record could stay valid in a cache, in a cache in a resolver, or in a cache in a name, in any cache name server. Finally, there is data associated with the resource record. One field specify of 2 octets specify the length of the data, and finally we have in the record the data associated with that RR. Then typically there are different types of RRs. The most important, in fact, is the A, and where the resource data contain IP version 4 address associated with the full qualified domain name of the resource record. But there are other types. For instance, the quadruple, that is 4 A's, that contain an IP version 6 address associated with the FQDN of the resource record. And there are several different types, not only A and 4 A's. For instance, any zone has one and only one record of type SOA, start of authority. We'll see which is the importance of this register in the zone. But any zone has one and only one SOA record, and there are other important records. For instance, the NS records, that is name server records, where the data contained in the NS records is the FQDN that identify the name servers, the authority name servers of the zone. Any zone has typically at least 2 name servers. One is primary and the other is secondary. But the NS type RR simply identify the name server of the authoritative name server. The difference between primary and secondary is performed only in the in some field of the SOA record. We will see that later. There are other type of RRs. For instance, the canonical name, the CNAME. In fact, the CNAME contain in the record data what we call the FQDN alias associated with that with the FQDN of the records. That is very useful because we could translate any name, domain name, another domain name. The CNAMEs are used typically for that. In order to transform domain name, a full qualified domain name, in another full qualified domain name. That is, in fact, an alias of the domain name of the resource record. And we will see that there are other RR types. The pointer, the PTR, the pointer that is used in order to perform what we will see later is the reverse lookup in order to obtain the FQDN associated with an address, not to obtain an address based on a particular FQDN. That is what we call a reverse lookup. And other type, for instance, the MX from mail exchange, where in this case the resource record data contain the FQDN, that is the domain name of the mail exchange server associated with the zone. In fact, with the FQDN of the record. That is typically, in that case, the FQDN that identify a zone, not necessarily a node within that zone. And finally, for instance, the text, the TXT record type, where the record data is in fact a text. This is, for instance, used in some applications like some security functions implemented in the exchange of mails in order to exchange in a more confident way the mail messages across the internet using the sender policy framework that is encoded in some type of text records. Then, but in fact, and there is perhaps other types, other record types, but in fact, the most important, remember, the most important resource records are the A record, the NS record, the SOA record, and well, the 4A record if we use IP version 6. Then, in order to better understand the different type of resource records, we could use a troubleshooting tool called NS lookup, name service lookup, that we could use in Windows and Unix, Linux platforms. If we execute this command, we could set, for instance, the query type as A in order to ask, for instance, information about the IP address associated with some particular domain name, FQDN. If we type, for instance, this FQDN associated with typically with the website of Fachhochschule Dortmund, we will obtain as an answer that the address of the website of Fachhochschule Dortmund is this IP version 4 address. This is something that illustrates how, for instance, some piece of information of this type is implemented in order to, for instance, identify the address of the website of the university. But there are other information, for instance, if we would like to know the IP address, the name and the IP addresses of the name servers, of the authoritative name servers of the Fachhochschule Dortmund University. Then we could type ns lookup, we set the query equal ns, and we type, in fact, the FQDN that identify the zone of the Fachhochschule Dortmund University. Then we could get that, in fact, there are at least two name servers called in that way. And in fact, this is NS resource record. This is another NS resource record, and this is an A record associated with this NS record, and this is the other A record associated with this NS record. In that way, we would get the information, the very important information, in order to look up names under the zone Fachhochschule-Dortmund.de. For instance, if we in this figure, in this topology, in this chart, in this figure, we could see how the address lookup is performed. I used the FQDN associated with the web server of Fachhochschule Dortmund. Then we ask for the IP address associated with the Fachhochschule Dortmund website. And then this resolver asks that information to his local name server. This name server, and this in fact is a recursive query. Then after this query, this local cache name server will ask the root server about this information. That is, he would like to know the A record associated with this FQDN. In fact, root don't have this information, but root knows that this information is under the top level domain. Then respond with the name server and the A address of the name server associated with the DE zone. Then after that, this local name server will query another iterative query to the server specified in the answer of the root server. And this name server then respond not with the information requested, but with the information about the name server and the address of the name server of the zone Fachhochschule Dortmund.de. Then finally, this local name server will query with an iterative query to this name server, and this name server will answer with the A register requested originally by the resolver. Once the local name server get this information, this name server will store this information in his local cache and answer to the recursive query to the resolver, sending the information requested. That is the record A associated with this domain name, with this full qualified domain name. Well, then the resource record called NS or of type NS, they are used in parent zone to delegate subdomains to authoritative servers for their child zones, and they are specified in child zones to indicate which are the authoritative servers for the zone. And the NS records contained in the parent zone must be the same as those contained in the child zone. That is, typically, if this is a parent zone and this is a child zone, the child zone has typically several NS records that identify which are the authoritative servers of this zone. But the authoritative name servers of this zone have to be stored permanently in the parent zone, at least when the name servers are identified with full qualified domain names that include the zone name. And in that case, the records, the NS records that need to be stored permanently in the parent zone are called glue records. And in what is important to know that is that the glue records that are must be the same as the NS records in the child zone. If not, some problem called as a lame delegation could occur, and then it's very important to avoid this situation. That is, remember that the glue records, the NS glue records that we need in the parent zone must be the same as those contained in the child zone. Then remember, lame delegation occurs when a server delegates authority over a zone to another, but the latter has not been configured as authoritative for that zone or is out of service. This is one case. Unnecessary traffic is generated over the internet and delays due to unanswered queries made to the lame servers. That is, sometimes the problems of performance in the internet are related with this kind of problem that they call, for instance, lame delegation, and not are not because there are two traffic and problems of queues in the routers, but it's a problem of lame delegation. Availability is compromised due to a false perception of redundancy. For instance, if you configure a zone, for instance, here, you configure two NS glue records. One, it's okay, functions very well because it's equal to one of the name servers that is really in operation. But the other, for instance, is a former name server, for instance, and here we already change this architecture and now have another name server, not the previous. And in that case, we will have what we call a false perception of redundancy, not only a problem of performance. Well, in this slide, we could see the information of this particular type of resource record called SOA, Start of Authority. I performed NS lookup of the SOA record of the Fachhochschule Dortmund zone. And we could see that this record has typically in the record data some information, and that information is the primary name server. That is, if we look, for instance, here we could say get the information of the different name servers, the authoritative name servers of the Fachhochschule Dortmund. But in fact, only one of those is the primary. Which is the primary? The name server that is configured in the primary name server field of the start of authority record. This is, for instance, the address, the mail address of the responsible of the administration of this zone. And in fact, in order to understand which is the mail address, you need to replace the first dot by an arrobas. Then you need to write a mail to hostmaster@condenserver.de. And those are numbers, very important numbers. The last one is very simple, is the default time to live. For instance, in the case of Fachhochschule Dortmund, all resource record could be stored 5 minutes in any cache memory, for instance, in a resolver or in a cache name server. But there are other 4 numbers that are very important to the synchronization, to the update of the information between the primary server and the secondary servers. This serial number is very important because this is the called serial number. This is the called refresh number. Always this is specified in seconds, retry number specified in seconds, and expire number specified in seconds. Then those 4 numbers are used in the synchronization of the secondaries based on the information stored in the primary server. We will see this in a couple of minutes. Well, finally, the reverse address lookup. The mapping of IP numbers to names in DNS is arbitrary. That is, any IP number, regardless of, for example, its net ID part, that is its network number, can be associated with any name in the DNS. That is, the naming is independent of IP number. For instance, if an IP address is in Argentina, that IP address could be associated perfectly to a name, to a domain name under .de. It's not a problem. Then there is no mapping between IP numbers and domain names, and we could assign arbitrary names to IP numbers. The location of a host in the DNS system is independent of the routing of the datagram. It's what I just said recently. That is, for instance, an IP address could be associated with to an interface in a router or host in Argentina, and we could use that IP address to be associated to domain name that is in the zone of, for instance, Fachhochschule Dortmund D. The authority in the domain in hyphen added the array. ADDR.ARPA is related to the physical connection. It is delegated according to the components of the IP numbers. And then what we need to perform is a reverse address lookup. That is, in the address lookup, we provide a name and we would like to get an IP address. In this case, in the reverse address lookup, it's inverse. We provide an IP address and we would like to obtain a domain name, a full qualified domain name associated with that IP address. In order to perform that operation, we will use the top-level domain ARPA and the domain name in ADDR.ARPA. For instance, in this example, using the nslookup command, I could set the query to PTR, pointer. It's one of the types of the resource records. And I could ask, for instance, I would like to obtain the name associated with the address 217.116.122.187. And then I need to construct the FQDN in this way. And that is, we reverse the address, the IP version 4 address, and we append as a suffix at the end of the FQDN the name of the domain in ADDR and the name of the top level domain ARPA. And in that way, we could obtain, for instance, this is the full qualified domain name associated with this address. Then this is the illustration of the reverse address lookup. We need to obtain the name associated, that is, we need to obtain the PTR, the pointer record associated with this address. Then we construct the query in that way. This number first, this number second, this number next, this number next, and finally dot in the ADDR.ARPA. And we ask for that FQDN. We ask for the name server, local name server, then the local name server will ask to the root server. The root server respond with the name server and IP address of the authoritative name servers of the ARPA top level domain. Then the name server will ask for the top level domain ARPA and obtain the name server and the IP address of the name server of the zone in ADDR.ARPA. The name server then asks to that name server, and that name server offer the information about the name server and IP address of the zone that administer this net number. Remember the net number. If this address is a class C address, the net number is coded in the three most significant octets. That is, this number dot this number dot this number. Then the administration of the names associated with the addresses that start with this prefix, with this net number, will be served by a server that one or more servers that administer this zone. This is a zone. This zone administers the addresses associated with this net number, Then finally, this name server will respond. Typically, this name server is administered by an ISP that is the ISP that received the assignation of this net number to assign IP addresses in the internet. And then this name server will answer with the PTR resource record asked or queried originally by the resolver. Then finally, the resolver receives the information, and the information is in fact the name associated with this address. That is this name. This name. Remember, we ask for the PTR resource record. Well, and here we will see how the secondary servers of a zone could synchronize or update the resource records from the primary server. Then, in order to perform that operation, for instance, if the administrative entity of this zone change, for instance, add, change, or delete some resource record in this zone, this is performed only in the primary server. But after the modification, after the change performed on the resource records of that zone, the secondary servers have to update the resource records of the zone that they have in their machines, in their hosts. Then each secondary server of a zone perform a refresh, that is x seconds, with a period of x seconds. In the case, for instance, the Fachhochschule Dortmund, the refresh is 8 hours. Each 8 hours, the secondary server, each secondary server of the Fachhochschule Dortmund will ask to the primary server for the SOA, or the start of authority record, and will read the serial number. If the serial number is the same as the previous serial number, that is the SOA that is stored in the secondary server, then nothing need to be transferred between the primary server to the secondary server. But if the serial number is bigger than the serial number stored in the SOA in the secondary, that means that in fact some change has been performed in the primary. Then zone transfer need to be performed. That is, all the resource records of the primary need to be transferred to the secondary. Or, depending the implementation, some implementation permit to transfer only the changes, and that is a transfer shorter and with less information to transfer from one node to the other. But there are other two numbers. For instance, the retry number is the number of seconds that we need to wait if, for instance, when we ask for the SOA record of the primary server, for instance, couldn't answer, or perhaps couldn't answer, or the secondary server couldn't receive the answer of the primary server, then the secondary server need to retry the query of the SOA to the primary server. If this retry, for instance, in the case of Fachhochschule the retry is 2 hours. The expire is 7 days. That is, if after 7 days we couldn't obtain the information of the SOA from the name server, this from the primary server, the secondary server will expire as an authoritative name server for the zone. Why? Because the secondary server is not certain about the information of that zone. Change could be performed during that expire time, and the secondary server doesn't have that information. Finally, remember simply that the zone transfer is, in fact, the resource records are transmitted over TCP, and the reserve port is 53 as the port of the server. Well, finally, we could talk about the DNS name registration, and that is, we already talked about the ICANN, the Internet Corporation for Assigned Names and Numbers, and we called about the NIS, Network Information Centers, for instance, the DENIC, that is the Deutschland Network Information Center. That in fact, this NIC is the NIC that administer the top level domain. But it is very useful to this protocol called WHOIS that was specified in this RFC, and provide information about the different zones. For instance, you could ask for the information associated to the Fachhochschule Dortmund zone, and you will see that there is four name servers that has authority of that zone, and in fact, this is the date of the last change of that information associated with that zone.